Welcome everyone to the IFIMAC-ICMM seminar series on condensed matter. I'm Laura Arriaga from Universidad Autónoma of Madrid, and I will be chairing this seminar today. Let me remind you first how we usually proceed during these seminars. If you have a question during the talk, please write it down in the chat, and at some point I will interrupt our speaker and I will ask the question on your behalf. Otherwise, at the end of the talk, we will have time for discussion, and at that point, you will be able to unmute yourself and ask your questions directly to our speaker. Please use the raise hand button so that I know that you have a question and I can give you the time for that. And now it is my great pleasure to introduce our invited speaker today, who is Professor Peter Schall, an experimental soft matter researcher at the Institute of Physics of University of Amsterdam. Peter did his PhD at Jülich Research Center in Germany, and later in 2002 he joined the group of Professor David Waits at Harvard University, where he had a very productive postdoc. And after that, in 2005, he joined the University of Amsterdam, where he's currently. Peter and his research group are making very significant contributions to the soft matter field. They are focusing on the study of the assembly of new materials and their mechanical and optical properties, which are governed by equilibrium and non-equilibrium statistical physics. And they are trying to bridge the different time and length scales relevant to these assembled materials. And precisely today, Peter is going to tell us about colloidal design and how they can build new molecules and materials at the micro and nanometer scale. So Peter, the screen is all yours whenever you are ready. Thank you.
Thank you, Laura. And welcome everybody. I'm super happy to give this Zoom seminar and tell you about the colloidal design. So what one can do nowadays with colloidal particles. Very nice that I can speak to you. I'm sitting in my office, in fact, in Amsterdam. You see that from the orange background, I guess, oranje. And I realize I'm speaking to a broad audience, and I hope to being able to offer something for, let's say, both soft matter as well as, let's say, the condensed or hard condensed matter physicists of you, because you can actually use, and I'm going to show that, these particles on a smaller scale, on a nanoscale, and build new functional materials that have really interesting optoelectronic properties. Okay. Let me go to the next slide. All right, so the idea is to use these particles, very sophisticated particles, in fact, to build on new length scales, on nanometer and micrometer length scales. And of course, in a big picture, as you see here, we have learned quite a bit in chemistry over the past 200 years and know how to build molecules and polymers. And on the other hand, we, of course, we know how to build houses, but there's some length scale in between that we are just learning how to build. And it's challenging. It has really its challenges in order to being able to cleverly, let's say, make particle architectures that may have properties, mechanical properties, or optical or electronic properties. And that's something that I'm interested in and I'm trying to address. Of course, I'm not alone. There's many in the past 10, 20 years. It's become a really rich field where many people have contributed. We can actually do quite a bit, and I'm just showing a few examples in the top row here from DNA-coated particles, where you essentially can encode some interaction, so quite specific interaction between the particles by attaching DNA strands and then essentially programming in which particle wants to bind with which one. Or another example here on the right, where you have patches. In fact, I'm going to focus a little bit on this later, where you have patches. It looks almost like a molecule already. So with the patches, you predetermine where other particles may bind. But there's a whole zoo of other really exciting techniques that people have used. So for example, look down here, ellipsoids that are half covered, so that form, we call them Janus ellipsoids, that form these beautiful filaments, or even nowadays active particles, so particles that can actually swim actively by themselves through a solvent and show new bridge phases. And here I'm showing an interesting example where you have essentially microcapsules that are quite flexible and adjustable, and you have attractive and repulsive spots, and these people show that they spontaneously assemble into kind of a virus structure. Anyways, there's many more examples, but yet if you really look, the challenge is still to realize complex structures. So if you look in biology, of course, you know, we realize that we are super far away from any of these immensely sophisticated, beautiful structures. I mean, just to put a few on the screen here, I think you know very well either proteins or even this bacteriophage or DNA. These are masterpieces from which we are really miles away. And of course, there are several reasons for that. One reason is, of course, that it is still hard to get equilibrium phases, so to control the interactions in a way that they're of the order of a kT or two, or maybe half a kT, and adjustable, so that you can actually let the system evolve in a true equilibrium manner. Another reason, of course, is that the complexity of these structures go down to essentially complexity of the quantum mechanical states of the atoms and molecules, especially carbon with its different hybridization states, etc., which are difficult to mimic. All these, for all these reasons, of course, we realize that with colloids we are far away, but we're making progress. We're making some steps. In particular, a technique or way to assemble particles to control their interactions that I am going to address is what we call solvent-mediated. First of all, that means essentially if you have, you know, oil droplets in water, this is already something that I would call mediated, because the oil droplets will aggregate, will form eventually an oil film, right? So the oil comes together because it doesn't want to be surrounded by water, but rather close to another oil. So it immediately aggregates. And of course, this is a super important principle in nature, which is already the very basic assembly method with which cell membranes or these phospholipid bilayers assemble. So essentially, you have these oily hairs, these apolar hairs, and you have these polar heads, and they spontaneously assemble into this bilayer. So this is one of the most central and most basic and most important assembly techniques that you have. But typically, though, if you would use colloidal particles, these hydrophobic interactions can be quite strong and quite uncontrolled. So you will not be able to easily get all the beautiful equilibrium phases. What we do is we do a special trick. We go closer to, let's say, the critical point of a solvent. I'm going to explain what that means. And with that, the interactions, first of all, can become longer range. And second, we can control them. We can make them much more adjustable. And somehow, because I will show you that this is known as the critical Casimir effect. It has an analogy with the quantum mechanical Casimir effect. This will link us somehow a little bit to the world of atoms and the quantum mechanical wave functions. We have now long-range, possibly long-range correlated interactions, and somehow we are sitting in between these two worlds, let's say. To make that a bit clearer, and maybe for the especially the condensed matter physicists among you, the effect is the following. Of course, the Casimir force is a well-known effect where quantum mechanical zero-point fluctuations, so vacuum fluctuations, are confined between two plates. And because there's a different mode spectrum between these two plates, that gives rise to this attractive force. We have here the thermodynamic analog. What this means is that the plates are not in vacuum, but they're sitting in a solvent, so in a liquid, and this solvent is near its critical point. What that means is that you get concentration fluctuations in the solvent. So for example, it can be a mixture of two liquids, and then you get composition fluctuations. It could also be just a gas-liquid critical point. Doesn't matter, this phenomenon is universal. Anyways, you're confining, again, fluctuations, and due to the confinement of these fluctuations, you get an analogous attractive force. And the nice thing is we can control that quite well. So here you're confining composition fluctuations of the solvent. And in a simple, let's say, phase diagram that you see over here, where you have on the x-axis composition, on the y-axis temperature, you have these two regions. You have a mixed phase here on top, and you have a demixed phase. What does it mean? Well, mixed would be like water and, let's say, alcohol that really like to mix. Demixed would be like water and oil that do not like to mix, that want to phase separate. And then there are solvents such as the one depicted here that are in between. So in a certain temperature composition region, they're demixed. In another one, they're mixed. And just at this top point here, at the critical point, this is what we are talking about. So this is where these long-range fluctuations arise, and where we can get essentially this nice control over attractions. Okay, and there's a beautiful physics behind it, because close to the critical point, you have all these universal scaling relations. One that I'm showing below here, look at this, the correlation length diverges as you approach the critical point. So there's a universal dependence of this correlation length on temperature. And mu is the Ising exponent. So we scale temperature, so the distance to the critical point. So there is quite some universality. Anyways, for us experimentally, it just means we have control over the interactions. For example, also between two suspended particles. So now we don't have plates, but we take the particles themselves, they confine the fluctuations, and we have an attractive force. All right, we have worked this out a little bit in more detail. Here's a sketch that you can see where we confine these fluctuations. We have worked that out with theorists from Stuttgart, Germany, Professor Dietrich's group. And these forces have a nice universal, let's say, form. You can describe them that, so the force as a function of distance, z, let's say, between two particles really depends just on a function that depends solely on the correlation length psi. R is the particle radius here. So this is nice. We have a universal dependence. And just to show you what the potentials may look like, here are some results of a combined modeling and experimental measurement. And you can see as we essentially approach the critical point. So if we go from blue to closer and closer to 0.5 Kelvin away, 0.4 Kelvin, 0.3, you see that we get this attractive minimum over here. So which means that we have really some tuning on the scale of a fraction or a few kT with which we can, let's say, change the particle interactions. Okay, and what does it mean experimentally? Let me now finally come to show you some movies. If we just use spherical particles, such as here, right, and we keep, let's say, approaching the critical point, what we see is that the suspension, these particles, they're first suspended. Now we are going to approach the critical point more and more. They're actually forming clusters, and they're forming small, what you may call liquid nuclei, small liquid drops, and these drops will grow. So what you immediately see in a model system is here a colloidal gas to liquid transition. So you see that particles condense due to an increasing attraction, and they condense into these nuclei that then grow into larger and larger drops. So this system we could already study in terms of a gas-liquid separation. In fact, you find, of course, the full phase diagram. So you start with the gas on the left-hand side, and then as you approach this critical point, you get stronger and stronger interactions. You move through the phases. So you get a liquid phase, and eventually also get crystallites over here. We did a bit of work on which I don't want to focus right now, just to show you what you can do, because these systems, of course, particles are of the order of a micrometer in size, so you can easily optically image them, as you see. You can even stack images. You can record three-dimensional image stacks and then reconstruct particle positions quite accurately, let's say with a typical 20 or 30 nanometer resolution. So really well. And then you can see how this phase transition happens essentially in 3 dimensions on the particle scale. So here, for example, we are still a little bit below, so we have still a gas phase. The red particles have a certain number of nearest neighbors, and you see when I'm essentially going across this transition, you have these larger droplets or condensates formed. And we could very well essentially identify the critical step here, which is the nucleation step. And just to give you a nice picture and example, we could determine the critical nucleus, what it looks like, how it fluctuates. We could even measure from these fluctuations the surface tension, the effective surface tension of this created nucleus, which in fact is not trivial. There's quite a discussion in the literature, if you look into papers, about what this surface tension, I mean, for real atomic liquid is. And the discussion evolves around that. Of course, you know it for a flat surface. If you have a macroscopic, let's say, surface which is flat, you know what the interface tension is, you can measure it. However, if you have a droplet that is, let's say, curved, at the scale or at the atomic scale, essentially you have less nearest neighbors, effectively a little bit less because of the curvature, and then the interface tension changes. But it's not clear by how much, so we could measure that nicely in this model system. Anyways, this is one example. What I want to get to is whether we can do and make more complex structures. Okay, and this is where we met people that are really masters in doing these sophisticated particles. For example, at NYU in New York, where they can make these particles that have patches that are, let's say, hydrophobic, and the matrix, the gray one, is hydrophilic, for example. This is what they can do. And we thought, well, maybe we can make a colloidal analog, a molecule analog with these colloids. Essentially, the idea is almost like with a wave function, but don't want to get too far, but you can confine the solvent fluctuations essentially between the patches, and that should lead to a very selective attractive force between the patches. Here is how, in a simple model system, here is how they actually do it by colloidal fusion. It's amazing how precise and also how monodisperse these particles are. Anyways, we leave that up to them. And then we can use these. So you get particles like with this technique that are dimers. So you get, you know, these 2 patches, or tetramers. You get 1, 2, 3, and 4, right, in a tetrahedral symmetry. And even higher orders, you can get particles with 8, I think, etc. Now, I'm going to focus on the di patch and the tetra patch. I'm going to show what we can already do with these particles. Now, if you just have them isolated, for example, the dimers, then they will assemble in these chains. And the movie is showing sometimes an optical image, sometimes only the fluorescent patches. So the patches are fluorescent, so you can see them, and you can see nicely how 2 patches are joined into 1 point. So they're really bonded, let's say. You can already see this is like a polymer analog that shows fluctuations even in its bending. You know, it has a bending rigidity, it fluctuates around. When we do that for the tetramers, then they will form these, of course, these angled, these zigzag configurations, and they form even much more, which I will going to show in a few minutes, many more compounds, I would say, that you know actually from sp3 hybridized carbon, making them quite interesting to study in real space. But let me first focus on the dimers, so on the chains, polymers that we get here still, and we can see, because the attractions are really of the order of a kT or a few kT, we have equilibrium conditions. For example, we can see like that a chain attaches, like at this green point over here, it's going to attach, and that it also breaks. This red point over here, it breaks. So we see both attachment as well as detachment. And we thought, and we can even determine, let's say, the bond lifetime, which is plotted here as a function of distance to the critical point. So once again, once I'm approaching the critical point from right to left, I have longer and longer, stronger bonds that are less likely to break. Okay, so I can tune these bond lifetimes. Now, these are living polymers with tunable bond probability, and we thought we just, I mean, it's just fun to test polymer theories. And these are quite simple. So let me first show you guide you through the experimental results. So here, what we have done is we have quenched the system very close to its critical point where the attraction is really strong and you get these very long polymers. Now, if we in steps go, stepwise down in the attraction, you see that you get shorter and shorter polymers. You get distributions until almost you have only monomers left. And these kind of equilibrium distribution are given by Flory theory, or we tested whether they're given. And then the length, let's say the probability to get a chain of length x is essentially given by 1 minus the bond probability times bond probability to the power of x minus 1. Why is that? Quite simple. If you imagine a chain and you pin down the first particle, which is not bonded to start with, you have the probability of 1 minus PB. Simply, it's not bonded. Now you keep adding the other particles, this one, etc. And this essentially gives you, each time you add the particle, you have to multiply with PB, right? Because you're bonding one more particle, and the probability for adding a particle is PB to the power of x minus 1, because you're attaching x minus 1 particles. All right. Now you can express that a little bit different, where you express this bond probability exponential minus 1 over the average chain length. Anyways, what you will see if you plug it in, you're expected to get a distribution of length that is exponential. E to the minus x over the average length of the polymer. And this is what we actually found experimentally. So here, plotting in a half logarithmic scaling, I'm plotting these length distributions, and you can see as we essentially getting stronger and stronger attractions, we get longer and longer chains. So initially, very short chains, the green one have longer ones, even longer ones. And in fact, you can use these average chain length that you get to back out the bonding probability, compare it with your essentially measurement, what I showed before of the average bond lifetime, and you find a really good consistency. So that shows that this, in a nice model, that this polymer equilibrium theory really works for these particles. All right. Also about, we were then looking at, but I'm not going to show, at polymerization in 2 dimensions, for example. There's still open question of how the polymerization goes, because if you have crowded polymers, they hinder themselves and you have kinetic arrest. This is currently under revision. But what I wanted to show you is that we can also tune the rigidity, the bending rigidity of these filaments. So here is a relatively stiff filament. If we go a little bit further away from this critical point, weaker attraction, you see it's much more, it's bending much more. And if you go even further away, you see it gets really fluffy, and at some point it even breaks. Here it has broken. You see it? You guess these modes. We actually did a full mode analysis of these different harmonics and higher harmonics that are thermally excited, and we could back out bending rigidities, etc. Here you see typical values of the persistence length as a function of this temperature parameter, and you see that we can tune it. In fact, persistence length is of the order of that of well-known biological filaments, for example, microtubules. And we can tune it with the attraction. Okay. Now, next we were adding a few 4-patch particles. So what happens if you do that? You have chains. Now you're adding 4-patch particles. You're introducing branching points. In fact, what we see is that we get an analog of a cross-linked polymer, which means now the polymers can bind to each other via this higher valency particles, and they form a space-spanning network, which we could, let's say, image and analyze in detail. And there's nice theoretical work about these kind of equilibrium networks and equilibrium gels that you can have. So now you can have structures that are not crystals, that are rather very open structures, very low density structures, yet they are still in equilibrium. And this is because the geometry is encoded in the particles. So essentially, here below, you see that you have a line of a polymer, you have a line, and then you have this crossing point. And this is, of course, everything is set by the local bonding geometry of a particle. So maybe not too much of a surprise, but you can get structures such as this. These are now really assembled colloidal structures where you can get these beautiful networks of particles. It looks almost like a cross-linked polymer network or a biological filament network. This is what you can do. And we checked, in fact, I don't want to get into detail about that. We checked, in fact, that indeed we can assemble them in equilibrium, so in terms of very fine temperature steps on the right, and versus we can quench them. And in fact, these two routes are identical. So here I'm just showing cluster populations as a function of bonding probability, and the symbols, these are for 1 particle, 2 particles, 3 particles per cluster, etc. And the symbols are both quench and equilibrium, and the solid line is Floy-Stockmeier equilibrium prediction. So you see that they nicely all overlap, which means here have a system where in equilibrium we get these very open structures, and it doesn't matter which route you go to this percolated state, because essentially the geometry, the network geometry is encoded in the particles. Okay, now let me change gears a little bit and just investigate 4-patch particles for now, because they have, of course, interesting analogues in chemistry, because they look really like sp3, let's say, hybridized carbon. Of course, we don't have quantum mechanics at work, but what we do see is geometrically equivalent structures from what you know in chemistry, essentially. So we get these structures that you may recognize as the carbon backbone of butane or butyne, or the cyclic structures down here. And we thought maybe interesting to investigate some of these cyclic structures and see what we can learn by looking at them in real space. And looking at cyclopentane, so having 5 particles, we saw something, of course, that chemists know, namely because the bond angles inside these structures are not compatible with the tetrahedral bond angle. There's a slight puckering of this ring, slight out of plane puckering, and chemists know that from spectroscopy, but have not seen it yet in real space, let's say. And of course, there's so many equivalent structures depending on which particle is up, which particle is down. You can make a whole circle of these different structures. So defining the phase tells you which particle is up, essentially, and the amplitude, which is given by the distance from the center of here. So the larger the amplitude, the further you go out. And we can look at these structures essentially in real life and real time, as you can see here, and we can follow this puckering motion essentially of the molecule, and we can see how it walks through phase space, which you see here on the left-hand side. We did a little bit of statistics about this, so plotting the frequency of occurrence as a function first of this phase angle, and of course this curve is flat because there is no preference for any. It's a what you would call pseudo rotation, which means it doesn't really matter. It has no activation barrier. It can just essentially pucker around the whole ring. Now, on the right hand side, you see essentially the frequency as function of amplitude, and this has a maximum. Look at the data over here, which is the experimental data. In fact, the orange curve is for actual molecules, atomic molecules. It's a bit different because it has a slightly different interactions. But the first increase comes from the fact that once you allow the particles to leave the plane, essentially you increase the entropy a lot. You have many more microstates because the particles now, there's many more states. But then this down curving essentially tells you, well, you have to pay a price named the bending energy. While you're moving particles out of plane, you're paying essentially an bending energy penalty. And this essentially makes the amplitude decrease as a function of increasing strain. And we could even back out from these measurements, that's in the inset here, what in fact the bending energy U as a function of this amplitude is. Anyways, we could get quite a bit of insight. And also, when looking at these rings, we saw that sometimes they were opening spontaneously. So we saw essentially a chemical reaction, so to say, an opening reaction of this ring. And we thought immediately of, let's say, catalysis, and we thought maybe we could investigate the action of an attractive substrate to this opening reaction. So how does it go when it has an attractive substrate? And in order to do that, what we did is we, instead of taking a normal glass, which you see on the left-hand side, we made the glass also hydrophobic, similar as the patches, so that the patches would also attach to that glass. Okay, so what we started with is these rings. We let them sediment on this attractive surface, and then we could see that within really a much shorter time, they would split up. So obviously, the surface really served as a catalyst. It accelerated the opening by a factor of, I don't know, 10 or even 20, much faster. And we are currently looking into a little bit more detail of how essentially this catalytic effect goes. How does the attraction of the substrate in fact speed up the opening of the ring? Of course, the attraction fixes the patches to the surface, makes the ring somehow more constrained, so that when it opens, it gains a lot of entropy. But we're currently looking into, let's say, the energy entropy interplay in this. And then you could think of different substrates to be used to study kind of geometric effects of catalysts. Now, in fact, this led us really nicely and by surprise to something, some different materials that we discovered by chance, but maybe not too much of a surprise. Of course, there is this whole class of two-dimensional materials in condensed matter physics that started with graphene and with the Nobel Prize. But of course, there's many, many more that evolved. I myself, I'm working on metal dechalcogenides that have interesting optoelectronic properties. Anyways, these are all layered materials. And in fact, when we take these simple colloidal particles attached to the surface, we can build very nicely two-dimensional materials. In this case, well, you can guess which of the representatives up we can actually obtain, because in our case, essentially one of the four patches binds to the surface, right? And then there is essentially three patches free to bind to each other, particles to bind to each other. So essentially, now we have turned the system into something that looks like an sp2 hybridized carbon atom. And in fact, no surprising, well, what you get is graphene flakes. So we saw that these particles that can still, let's say, that are attached with their patch at the surface, but they can still diffuse along the surface. They actually form very nice assembled graphene-like flakes, crystals. And, you know, this, in a sense, beautiful. You can study this assembly process now in detail. And I think there's still a number of big questions. How do you actually get large graphene feeds? How can you grow them? And with this system, in principle, it can serve as a model system to study that. Even more surprisingly, we then discovered that this was simulated, in fact, by somebody you may know in Madrid. Eva, maybe you're even here in the audience. Then speak up, but maybe not.
No, she's not.
She's not. Okay, fine. But anyways, there is collaboration where Eva and collaborators had already simulated a very, very similar system. And it has actually quite a nice complex phase diagram that I just want to highlight for a minute. In addition to the honeycomb phase, which is HC over here, the honeycomb, in addition to that phase, you have a vapor-liquid phase, of course, vapor and liquid. And then you have an even denser liquid, which I would call actually an amorphous phase. And you have a very dense tetragonal phase, T. Well, how does that come about? Honeycomb, I think, is clear. The liquid just means you keep, because this is a function of density, the x-axis, you keep adding particles, right? And you get these amorphous structures that are more dense than the honeycomb. The honeycomb is quite open and not very dense. So if you keep essentially increasing the density, eventually what you end up with, that you fill all the honeycomb spaces with a particle, and then you get a trigonal lattice. And in fact, experimentally, we could very much confirm that. So starting from the honeycomb, adding more particles, we get something amorphous, and we could even see the trigonal phase, which you see here by these bottom particles. You see it has these triangles. It's something we are currently writing up and thinking already. Maybe you have also suggestion, maybe some of you working in this field for atomic graphene. We're thinking about visualizing graphene formation or even defect motion or defect healing. There's a lot, I think, that we could look at. This is to come, and would be happy for suggestions. All right. Let me, in the last few minutes of the talk, move more towards condensed matter, namely exploring particles which are now semiconductor colloidal particles in order to build functional optoelectronic materials. And the idea is simple. I mean, the field has a big hype right now to also make very sensitive photodetectors or even solar cells. The thing is that one of these nanoparticles, so we are now going into the nanoregime, so a particle between 5 and 10 nanometers, say, is confining the electrons like an electron in a box, so that the electronic wave functions become quantized. Essentially, you can have only multiple of these wavelengths, as you see over here, lowest energy and a higher excited state, etc., etc. So essentially, you have made a model atom that has, with a set of energy levels that you can design, because as you know, by changing the size, you will change the distance between these energy levels. And in fact, this is what you see in the background. So if you look at the fluorescence of these particles, for big particles where the energy levels are close together, you get this red fluorescent light, because low wavelengths and long wavelengths, low energies. And as you make them smaller and smaller, essentially the energy levels split up and you get this higher or bluer light. Higher energy bluer light. So essentially I've made a nice model system that you can tune. And the next step, or the idea is, can't you, like you did do in condensed matter, where you take the atoms, essentially assemble them or make crystals, and then you get new states, bands, energy bands, can't you do a similar thing with these model atoms? So essentially you put them together in a compound and, starting from essentially a single atom going to a molecule, you split up the energy levels, right? If there's sufficient coupling, going to full crystalline solid, you would be able to make bands, right? Band structures, but with an entity that you can engineer, that you can control. and then you would make a quantum dot nanocrystal solid, essentially, new material out of that. What we have done, let me just show you this one. You can quite easily assemble these nanocrystals into a larger supercrystal. And you see an example here. The way you do it is you're using an emulsion. So you have the nanocrystals essentially submerged in oil with water. You shake it. It's really a simple process. I think in soft matter, people know how to make emulsions. You know, they know how to make mayonnaise, etc. So this is all the same process. You emulsify, which means you disperse these droplets, and then you slowly let the oil evaporate, so it compresses the particles into denser and denser structures. And if you do that slowly enough, you end up with this very beautiful, ordered crystal, essentially. We were even doing X-ray experiments, but I'm not going to go into detail. Let me outline the idea behind it. So if you go from individual nanocrystals to these supercrystals, to these assembled ones, the individual ones have, let's say, two challenges or disadvantages. The first is that the interaction with light is small, because they're nanometer scale, they are in the Rayleigh scattering regime, so there's not much interaction. So their cross-section will be the normalized, so divided by the geometric cross-section, will be quite small, much smaller than 1. And also the charge carriers that you might create by impinging light, they're localized, they're not going to travel. However, if you go to superstructures, so you have many of these nanocrystals inside, then first of all, you're in a different scattering regime. So the absorption and the cross-section is much larger. Actually, it's getting of the order of 1. And second, if you have sufficient coupling, you can actually make these excitons move across the structure. You can have conductivity, maybe bands. And this is something we were looking into essentially last year and the year before. And first of all, we investigated the photonic coupling, which means now you have this much bigger entity, which has an effective refractive index, here denoted as N. And this much bigger entity has a strong interaction with light. And you see the resonances, the photonic resonances here. So depending on the size of the sphere with respect to the wavelength, or let's say the new wavelength, so lambda divided by the refractive index, the effective wavelength. If you're 1 times of that, or 2 times of that, or 3 times of that, you get all these increasing resonances, essentially, these modes, photonic modes inside. And you see that as a function of that, you get these ripples, essentially. So this is where you get a new mode in. And you see now that for certain diameters and for certain wavelengths, that's the color over here, for certain wavelengths, you actually can get absorption cross-sections, essentially going up here. You can get absorption cross-sections that become larger than the geometric cross-section, which means you now have a structure that actually attracts the light, that funnels the light into it. So if you want to build efficient, let's say, solar cells or even photodetectors, this is quite advantageous because you can trap the light, essentially. You can get it. Now, the second point, the excitonic coupling, is essentially, we could investigate that by transient absorption. What people do is they launch first a pump pulse, as shown over here, optically, so they pump the system, and then with a second probe pulse, they see which energy levels are occupied. So essentially, in a nutshell, you have the semiconductor with a valence band and a conduction band. And first, a high energy pump, you pump it deep into the conduction band, and then some delay time later, you let the charge carriers relax to the band edge or higher energy states, and then second, with a wide light, so with a broad wavelength, you launch a probe pulse and you see which light is absorbed. So you can determine essentially which states there are. How it looks in practice is the following: as a function of wavelength and delay time on the y-axis, you get certain states. First of all, the band edge state over here. So this is in fact, just the state here at the conduction band. Okay, and you see that just below that, at longer wavelengths, so at lower energies, just below, you get a bound state, which we identified as a bi-exciton. So now, essentially, two excitons have come together into a bound state. Okay. In fact, we could see now that as a function of coupling and of the size of the structure, we see that this bound exciton can actually vanish. If we have individual nanocrystals, this is sample 1 and 2, essentially, you have the bound bi-excitons and they cannot separate. So essentially the excitons cannot move or travel far. However, if we make larger and larger superstructures, and we even make the ligands shorter so that the coupling is better, you can see that this binding energy vanishes, which means now we're going over from a bound state to a conductive state, or to a state where the excitons can spread in space. So we have achieved, let's say, the transition to free excitons, or to coupling, essentially. I'm about to finish. Let me just give you a little bit of a bit newer material that we are currently investigating. These are these perovskite nanocrystals. They have become very famous, and because they're quite tunable, and people want to make real devices with those. They also have a very dense packing, as you see here. You have these cubics, the structures that assemble in a tight compound, and we can make these superstructures. And we found, I'm not going to go into details, that in fact here we also see a transition to completely conducting material. And why is this important? Because people are trying to make photovoltaic devices with that, so solar cells. And I'm showing you just a very massive chart, which comes from the Renewable Energy Research Institute, NREL, in the US. It's very complicated over the time, over many, many years, from 1975 to 2020. You see the cell efficiency for many different materials. Let me just block many of these materials and just show you two. There is the traditional silicon cell that some of you may have on the rooftop, and it performs well, but its efficiency essentially has saturated over, let's say, it cannot get any better, at around 24%. And there's also a thermodynamic limit that doesn't go. There is these newer cells, the quantum dot cells, materials that I've been just showing you, that are really on a very steep rise. They're still below the efficiency of the silicon cell, but I guess that in a few years, if this trend continues, and also physically meaningful, they can actually overcome the silicon cells and lead to greater efficiencies. And this is what people currently in this field are working towards, getting essentially efficient light absorption, efficient conductivity, to make better solar cell devices. Okay, there's been a very promising one published a few years ago in Science, in fact. All right, I think this brings me to the end. You were very polite not to interrupt me, so maybe you can have questions now. So yeah, I think I've shown you that with finely tunable interactions and these sophisticated particles, we can build, let's say, a bit more complex structures that have their analogues with molecules, can even design mechanical properties. And if you do it on the nanoscale, you can even create new materials for optoelectronic applications. Thank you very much for your attention, and please do feel to ask questions.
Thank you very much, Peter, for such a wonderful talk. Now we have time for questions. You can use the raise hand button if you want, or just unmute yourself. Fabian, please go ahead.
Yes, did I see it right that the graphene you did experimentally, like from the colloids, was still done with the tetramer? Yeah. And not done with the trimer? What is the problem with synthesizing the trimer particles?
I think geometrically, the way it's done, you cannot get 3 patches somehow. I haven't really thought about this. Our chemists have, but they tell me you can only get 2, 4, and 8 patches from this kind of fusion protocol. Probably, if we think a little bit about it, we will get why it is. But yeah.
Okay, thanks.
So it was a coincidental discovery that, of course, if you attach 1 patch, then you have 3 left, and then it works.
Yeah, but then of course you will have extra strain in the system, so it's not like
that's right.
Not like
exactly.
a real sp2 then.
Yeah, okay. Especially because the remaining patches are still pointing a little bit upwards. Yeah, it's correct. Yeah.
Okay. Thanks.
Any other question? Walter, please.
Yeah, thank you very much for your very interesting talk. And I also enjoy the seminars on solid state physics. At the moment, it's very difficult to attend such seminars. I have a question to this critical Casimir force. So if I understand you correctly, first the interaction you get the clamping of the molecules because they are critical density fluctuations. Yes. And finally, they bind because of the molecular interactions.
I think there's always these density fluctuations in between. Let me just try to go back a little bit, because the range of interaction we have in our system, because we are still some distance away from the critical point, is actually quite small. So if you look here at the interaction potential, this is the R is scaled by the diameter of the particles, which is, let's say, a micron or 2. You see that this is of the range of the potentials of the order of like 20, 30 nanometers, right?
Yeah, okay.
At this distance to the critical point. You can make it larger, which means I think that in the images I showed you of the chains, you will not see that distance. It's below optical resolution. But I do believe that at any point in time, you do have these critical fluctuations between these patches. So they're not really physically attached in a sense, but there is still this solvent in between.
Okay, yeah, okay, because 20 nanometers is large compared to the length of molecular interaction, which is only 1 or 2 nanometers at most.
Yes. Yes. And this is what, because you approach the critical point. So these 20 nanometers, in fact, are of the order of the psi, the correlation length. And so as you approach the critical point, and of course you could argue, we are still in certain dimension, we are still far away from it, but we're approaching it. You then go up essentially the line, and you get much larger. So you get from atomic scale interactions to extended interactions. Okay. That is the critical scaling. Yeah.
Okay, thank you.
Mm-hmm.
We have another question from Emanuela Bianchi. Please go ahead.
Hi, nice. So nice
to see you.
Nice to see you too. Nice talk. It was really, really enjoyable, and a lot of news results. I was wondering, so you mentioned this idea of studying the defects in the colloidal Kagome with respect to the defects in graphene. And I was wondering if you have already observed in your samples the characteristic defects of graphene, or like these waves defects that can happen in graphene.
Let's say you may be more expert in there, Emmanuel, because you did beautiful simulations on patchy particles, right? I think we are currently reading into the literature. So what you easily get, of course, already kinetically, at least that's what we see in experiments, is that instead of the 6 rings, you get 5 and 7 rings. And the 5 rings can be actually quite numerous. Simply because you don't need the 6 particles, so kinetically you're faster in a 5 ring than in a 6 ring, let's say. And we do see that there's changes between 5, 7, and 6 ones. So there is, diffusive attachment, detachment. So this is what we have seen. And this may be, I think this is also characteristic in atomic graphene. but you know better actually. I don't know.
You know what? So I'm asking this question because I was also at some point trying to look at these defects. And I had the impression from the literature that these defects in graphene layers are kind of related, or they're governed by torsional interaction. So usually when, well, you know, I see it from the modelization point of view, you usually have effective pair interactions that do not consider the torsional part.
Yes.
And I understood that this stone whales defect that decouples the 6 rings into a pentagon and a heptagon, it's due to the fact that there is a disadvantage of being in a heptagon or in a pentagon, but it is a relatively bad disadvantage because of this torsional contribution. So I was wondering if you, because I guess you have not this torsional contribution in the experimental system, because these are probably very short-ranged interactions.
They are, but you have this distortional contribution in the sense that there is, of course, an optimum of binding, right? There's an optimum of binding, which means that if you want to bend a bond, it costs energy, also in experiments, and this is what we see. So in fact, we do see torsional energy penalties. Yeah, this is also why this puckering, you know, this puckering of the cyclopentane has a penalty, because as one particle lifts up, it causes torsional strain essentially. Yeah, we have that. Yeah.
Okay.
And we could clearly measure it in these chains, in the polymers. We were really looking at bending fluctuations, etc. So I think this is all there. But I'm currently trying to grasp what the big questions, so similar as you said, are in the atomic field.
Yeah. So because I was trying to look at that. So also the idea of, so my idea was just to have a perfect layer and then take out or put in one additional particle, because this is what happens, as far as understood, in graphene layers, that there is especially there is an additional atom that's coming into the crystal, and then it has to rearrange. But yeah, I don't know. So that was my feeling when I was approaching this graphene literature, which is quite massive. So good luck.
Yeah, well, maybe we can come back to that. A student is, I think, in some time in the future, we'll look at that. So
okay, that's
interesting.
That's cool, because we can see it easily. So you can see it easily. I cannot. That would be quite cool. Thanks.
Thank you. Great.
We have a couple of more questions in the chat. Alexis, do you want to ask yourself?
Yes. It was right at the beginning. I didn't quite get how do you synthesize the patchy particles, and how do you determine how many bonds they form? So just by adjusting the diameter to the range of the potential, which is temperature dependent or something like that?
Yeah, so we haven't done it. So we left that to our colleagues in New York. But in principle, how it happens is that you have these, look at the top here.
Yes.
You have these particles that can actually yield and deform, especially the blue one. Now what you do is you confine them again in an emulsion drop, right? Similar as what I've shown in the end of my talk. And of course you have all different kinds of emulsion drops with 4 orange and 1 blue and higher number or smaller number, and then you're going to evaporate the emulsion drop. You're compressing essentially this whole system, and you're squeezing out this blue material, which is kind of fluid. So you're squeezing that out. So the result of that synthesis is that you have various different particles depending on your starting droplet, and you can have, if you start, I guess, with 3, this is shown here, right? Then you get this dye patch. If you have whatever 4, you get these 4 patches, etc. So you get a whole mixture of these, and then you have to somehow separate them.
Okay, thank you.
Yeah, and the separation is tricky. So you get only so pure You do it by centrifugation many times. Yeah.
Luca Bergamini, do you want to ask yourself to Peter?
Yes, I mean, if I can ask by myself, do you hear me?
Yes. Yep. Yes.
Okay, so my question is actually a silly question. It's about the ring formed by patchy particles. And in one of the movies that you showed, you see this kind of ring, which at a certain point it opens, like one
right.
in one part is like the particle are detached from the other.
Yes,
and it kind of open, and then subsequently the ring close the gap again, so it closes again. And so
this was probably just a repeat of the movie. It opens, and this is just the beginning again.
Okay. So
I mean,
so they remain like taken apart. So the ring it remains open after the detachment.
Yeah. And typically it would remain open. Of course, there is some chance that it also closes again, but typically once it's open, you see that it. Thing that I didn't say is, I skipped over that, that the ring typically opens at the place where there's the highest amplitude. So essentially the circles in here show where the puckering occurs, and the line shows where just after that frame the breakage has occurred. And you see there's, for all the different 4 different experiments, there is coincidence. So it seems there's really a stress on the system due to puckering, and when the stress is large enough, it opens.
Okay, thank you.
Thank you.
So Olfa is asking our last question.
Yeah.
Please go ahead.
Hi, thank you very much for a nice talk. I was wondering if you could also, using those same patchy particles, reproduce large 3D structures, like 3D crystalline structures, like what is done, for example, with dusty plasmas, to observe how defects evolve in such large 3D structures.
Yeah, yes, you can do that. I mean, already with, let's say, spherical particles, you can get simple crystalline structure, so simple hexagonal closed packed or FCC or so, you get that immediately. And then also, let's say, the weight of the particles, so non-density match, right? So that the sediment doesn't matter. But in this case here, actually, we have space experiments coming up. So in order to completely avoid gravity, with NASA, we have a few samples on the space station, which are going to be examined in a month or so. Let's hope for the best. And then you can actually do it really in 3D in the correct sense, that you have no gravitational force, so you can do it under ideal conditions. But indeed, you can scan through a whole layer of, well, typically 50, 60 particles deep. At some point, you lose the contrast, right? Because you need to look through many, many interfaces. But you can look like 50 to 60 particles across, yeah, in bulk.
So if you need microgravity time, I assume, what are the time scales? I mean, if you need the ISS time, I guess there are large time scales to make the crystals.
Okay. I mean, the most serious time scale is getting the samples up, of course, but that's not what you're asking, you know, and getting it shifted and shifted. That takes years, of course, but no. So the thing is, we don't know yet, and that might be actually a seriously limiting factor. We will only know when we do it. The thing is that, of course, I guess we could simulate it, but because for these patchy particles, the orientations need to be also right. So it takes much longer time for these patchy particles to bind than it would be for isotropic particles, simply because you need the rotational diffusion for the 2 particles to encounter their patches and bind. And that actually makes the time scales even much longer than they would be anyways. Yeah. But let's say, I mean, the diffusional time scale, of course, is the same as down on Earth. So we kind of know what it is. but the patchy particles make this process even slower. Yeah.
Okay, thank you very much.
Thank you.
Okay, now the last for real, Francesco Boccardo is going to ask you.
Yes.
Can you hear you? Yes.
Can you hear me? Okay. Yeah. Sorry. Just a very quick question. I was wondering if you have tried, or if it would be possible to see how the binding and the assembly of these particles would be affected by an external bias, like, for example, a thermal gradient with a thermophoretic force, or an electric field, or something like this.
Yeah, actually, we are doing both at the moment. So the answer would not as short as the question. Okay. But what we are particularly doing, and maybe to highlight, is the thermal gradient. And the reason is that we actually want to grow large graphene crystals right now, colloidal graphene crystals. So we imitate what people do in atomic growth, like temperature gradients, right? So they have like different crystal growth methods, all involve a temperature gradient. So you have, in fact, only on one side are the attractions strong enough, so you get us to start with a nucleus, and then you can move this gradient through the sample, and you hope that you get a crystal crystal. This is something we're actually doing right now. Let's see whether that works. And with electric fields, of course, you could align the particles or so. There's a lot of things you can do. Yeah.
Okay. Thank you very much.
Thanks.
Okay, I would like to close the session thanking again Peter for such a wonderful talk, and all of you for the great discussion.
Yeah, thank you.
Let me mention as well that we will have another talk next week on Thursday, 12 p.m., usual day, usual time, that will be given by Rafael Sánchez from Universidad Autónoma of Madrid. And he will be talking about quantum thermoelectrics using interference, entanglement, and non-equilibriumness. So please join us.